Let's begin, and we are talking about right now. The topic is the Metropolis Algorithm. Okay, and again, the idea behind the Metropolis Algorithm is that we are going to design a Markov chain by defining its transition matrix. Okay, so this is what we're doing, the Metropolis Algorithm. Okay, and we are designing a Markov chain by designing its transition matrix so that the stationary distribution of the transition matrix is equal to our target distribution. Okay, or in some cases you might not have a transition matrix because you'll have a continuous variable. Okay, but the idea is we're designing some kind of transition probabilities so that the stationary distribution is equal to our target distribution. Okay, so so we have some kind of target distribution. Okay, and we will say the PDF of the target distribution we'll call P of x. Okay, so P of x is the target PDF, and when we run a Markov chain, we'll say the value at time t. Okay. Value at time t is x super t. Okay, all right, and so the way the Metropolis algorithm works is that we will propose a new value using a proposal distribution. Okay, so we propose a new value using a proposal distribution. Now, on Monday, we looked at this idea of hopping from island to island. Okay, so for the island hopping example, okay, the proposal distribution was is we can propose one less than our current value, okay, with probability equal to 0.5, or we could propose one larger, okay, the island above, with probability equal to 0.5. Right? And so here, what we would say is, we call our proposal distribution g of x given x at time t. Okay. Okay, and so so the x value will be, x t minus 1. X can take on these two values, and the proposal probabilities for each of these things is 0.5. All right, so that's one one possible proposal distribution. You can have all kinds of proposal distributions, okay? This is just one example. Is this okay? This notation, this is proposing some value x given that we're currently at xt. All right. Other possible proposal distributions. You could say g of x given x at time t is equal to kind of the normal PDF with mean equal to x at time t and standard deviation equal to some arbitrary value sigma. Right? And so now you will propose continuous values. Okay? So if you are currently at say x at time t is 2, okay, you might propose 2.5 or 1.06 or negative 0.1, right? And so you have a normal distribution centered at 2, and you've got some kind of standard deviation sigma, okay, that you've arbitrarily chosen. And every time you update, where your normal PDF is centered will change, okay? The proposal distribution will update its center. There's no apostrophe there. We'll update its center with each iteration. Is that okay? All right. All right. Maybe another possible proposal distribution, and it doesn't have to be any of these things, okay? But will be that x will come from the uniform distribution, all right? And let's say we want it centered at x at time t. So what should our uniform distribution be? Uniform from, you can do x at time t minus 1 to x at time t plus 1, okay? And then you'll just propose any values from, if you're currently at 2, you'll propose any value between 1 and 3 with equal probability, okay? All right, so the Metropolis algorithm requires that the proposal distribution be symmetric. All right, and what that means is that the probability of proposing one value given some other value is equal to the probability of proposing it the other way around. And let me just kind of expand on this idea of having a symmetric proposal distribution. All right, so the coin flip example is symmetric. You hearing music also? Okay. All right, so the coin flip example is if we are at island 3, we propose island 4 with probability equal to 0.5. All right, and then if we are at island 4, we propose island 3 with probability equal to 0.5, okay? And so the probability of proposing 4 from 3 is the same as the probability of proposing 4 from, what did I say? The probability of proposing 4 from 3 is the same as the probability of proposing 3 from 4, okay? If we have a normal example, in that we've got g of x given x at time t is equal to basically the normal distribution centered at x at time t. Let's just say sigma is equal to 1. Okay, then okay, if x at time t is 2, all right, so let's say the probability of proposing 0.75, I don't know what this is, I need R to tell me, will be basically d norm of 0.75 given that the mean is 2 and standard deviation equals 1, okay? And likewise, if I just take this same curve, all right, and if I center myself at 0.75, what's the probability that I propose 2? These should be exactly equal. It's the same as the PDF of proposing 2 if I'm currently centered at 0.75 and the standard deviation is equal to 1, right? So d norm, probability of proposing 0.75 if I'm currently at 2, given 1 is that, and the probability of proposing 2 if I'm currently centered at 0.75 with a standard deviation 1 is also exactly the same. All right, so that's what it means to have a symmetric proposal. Okay, we can relax the this symmetric requirement. Okay. And if the probabilities are no longer symmetric, we get something called the Metropolis Hastings algorithm, okay? All right. If the proposal distribution is not symmetric, okay, we can use this and we get the Metropolis Hastings algorithm. Okay, so that's to say that g of x at a, of proposing a if you're currently at b, does not equal to the probability of proposing b if you're currently at a. Okay, so anyway, all right, but let's just first go back to the Metropolis algorithm, and then I'll talk about the Metropolis Hastings algorithm. Okay, so we're going to say we are currently at x at time t, okay, and then we propose x star from our proposal distribution. And then we calculate the probability of moving, which is going to be the minimum of the probability of the proposed value, x star, divided by the probability of the current value. Okay, so we look at the probability of the proposed value divided by the probability of the current value. If the proposed value is greater than the current value, then your probability of moving is exactly 1. And then if it's less than 1, then that's going to be our probability of moving. Okay, so these values of probability of x star come from the target PDF, okay, or PMF. So whatever your target distribution is, that's what's going to determine these P star values. Okay, and then generate a random U to decide whether you will move or not. Okay. All right. So if you move, then the next value, x at time t plus 1, is going to be the value you proposed. Okay. And if you do not move, then the next value, x at time t plus 1, is equal to the current value. The current value gets used again. And that's the Metropolis algorithm. So there's some really great stuff about the Metropolis algorithm, okay? So here, to calculate the probability of moving, what do we need? It says we need to get the PDF or the PMF of the target distribution, okay? But technically, you don't actually need the exact PMF or PDF of the target distribution. You only need something proportional to it, okay? So let's say we're in a Bayesian situation where we haven't calculated the marginal probability, okay? And so let me just kind of take a look at this. So right now we have P move is equal to 1 divided by probability of the proposed value x star divided by basically the probability or the PDF of the current value. Okay, so this is probability of the proposed divided by the probability of the current. Okay, if let's say so P of x is the PDF, meaning that the integral of P of x over all of the x equals 1, right? Okay, but we might not know P of x, okay? Let's say we only know, say, f of x. F of x, which is proportional to p of x, okay? Or in other words, is f of x is equal to p of x divided by z, but z is unknown. Okay? So we can say, I'm sorry, not, I wrote this backwards. F of x divided by z is p of x, okay? But z is unknown. All right, so what we can do is we can say p move is going to be equal to, the min of 1, and we've got 1 over z times f of x star divided by 1 over z times f of x current, right? And because we're calculating this ratio, these unknown constants just cancel out. And so you can calculate the probability of p move even though, even if you don't know the exact PDF, you only know something proportional to it, okay? Okay, so you can calculate, so you can still calculate p move without the proportionality constant. Which is frequently the case in Bayesian problems, where you have the likelihood and you have the prior, but you haven't bothered calculating the marginal because that required you to integrate or sum across all possible cases, right? Okay. So that's kind of neat, right? Okay, and then there's another part that's great, okay? The other part that's great is, so let's say our target distribution, oops, all right, I don't know what to do. This is hard to draw, okay. Okay, so let's say our target is the normal, okay? Now this is silly because okay, and let's say we start off in a region like way out here, okay? So let's say x at time t is like -40, okay? If we were doing just plain old like rejection sampling or something like this, okay? Anytime we propose a value, we're gonna just kind of like reject it because you should never be getting values like -40 from the normal distribution, okay? But here's the thing, okay? At x at time t, we will just generate some kind of proposal, okay? So let's say we'll use a uniform proposal. Okay, so we are at -40, okay, which has pretty much a 0 probability, okay, but not, I don't know, what is d norm of -40? Ah, okay, I need something bigger than 0. D norm -30. Okay, all right, so let's say we're at -30, okay, because 0 will break us. Okay, so we're at negative 30, which again, should still like never happen under the normal distribution, okay? So we use a uniform proposal, and then let's just say we propose so that the next value we propose is going to be a uniform value, is uniform from 1 less to 1 greater. Okay, so I can propose any value from negative 31 to negative 29. Okay. Okay, I don't know what I'm going to propose, all right? But here's the thing. If I propose negative 31, okay, let's say I propose negative 31. Will I move in that direction? So let's pretend I propose negative 31, okay? So what's the probability of moving? P move will be the minimum of 1 and basically d norm of minus 31. That's the PDF of my proposed value. And I divide that by the PDF of my current value. So I'm going to do d norm minus 31 divided by d norm minus 30. Okay? I will only accept negative 31 with a probability of 10 to the minus 14. Okay? Which means I'm not going to accept it, right? So this gets proposed. If I propose negative 31, I'm not going to go in that direction. Okay? However, if I propose anything greater than minus 30, right? Like negative 29.8, negative 29, anything like that. So if I do d norm negative 29.8, okay, and I compare that to d norm negative 30, it's like way bigger than 1, okay? And so what's going to happen is that, you know, if I propose anything less negative, or I'll just say anything between minus 30 and minus 29, I will accept it for sure, right? Probability 1, because if we do d norm, basically minus 29 versus d norm minus 30, this is going to be, the minimum of this is going to be 1, okay? So what happens is that in the beginning, even though I started off at this terrible starting location, the Metropolis algorithm will always accept moving in the direction of greater probability, okay? Sometimes you take a step backwards, okay? Sometimes, like if I proposed, instead of negative 30, if I proposed negative 30.1, okay? I might go there with a probability of like 15% or something, okay? So sometimes I take a step backwards, but in general, anytime I move towards an area of higher probability, I will go in that direction. So it's only going to take like maybe like 50 or 60 iterations to kind of, I don't know, maybe more than 60 iterations, but like you run it like 100 steps, you're going to be in this kind of the region of like a reasonable value from the normal distribution, okay? So the Metropolis algorithm always accepts if the proposed value is more probable. Okay. And it's just sometimes you don't propose values that are more probable, okay? Does that kind of make sense there? And so the really nice thing about the Metropolis algorithm is that you can be in a situation where you really have no idea what the target PDF should look like, okay? You have, like, you're in kind of this Bayesian situation where you have a likelihood and you have a prior, and you have kind of a formulation of it, but visually what it looks like, you're not sure. What's a good starting point? You're also not sure, okay? So you just pick somewhere arbitrary, and it probably has terrible probabilities, okay? Incredibly low. However, you just propose some value nearby, okay? So I'm thinking, so in the one-dimensional case, it's simple, but even in a higher dimensional case, you just propose something nearby. You have some kind of proposal distribution. You propose a value, and if it's more probable, you're going to accept it, okay? And every time you propose something more probable, you're going to keep accepting it. And then, and even if you propose something less probable, so if you propose something less probable, you're probably not going to accept it, but you might every now and then, and that just kind of helps you avoid this idea of like getting stuck in some local maximum or something, okay? But the Metropolis algorithm, anytime you propose something more likely, you're going to take it, and because of that, you will eventually end up in a region of high probability, okay? And then the values that you generate from the Metropolis algorithm will look like the target distribution, okay? That values of high probability will be generated frequently in your final chain, and values that are less probable will not appear as frequently, okay? Let me talk about the Metropolis Hastings algorithm. Okay. All right, so the Metropolis Hastings algorithm does not require the proposal distribution to be symmetric. Okay, and so the way that works, okay, it's exactly the same. So we're going to call this the MH algorithm. Okay, so we're going to start at x at time t. Okay, we have target PDF P. Okay, and then we have proposal distribution G. Okay, and then and so we have proposal distribution this, and so we propose x star from G. Okay, and what we have is that the Metropolis Hastings algorithm is that G of x star given x at time t does not necessarily equal is not symmetric. Okay, so what we do is we adjust the probability of moving. Okay, so we calculate P move as being the minimum between 1, and then we take the proposed divided by the current, and then we adjust for the fact that these things are not symmetric, okay? So the star given exit time t. Right. So we will go there based on proposed divided by current, okay? But that ratio is factored in, okay, is kind of weighted by kind of the relative probabilities of how likely are you to propose this value versus how likely are you to propose it in one direction versus the other direction. Okay, so if you're so let's say this probability is very high, okay, then we should accept it, okay? But we might put on the brakes if our proposal distribution is kind of biased towards generating that particular value, right? And on the other hand, this if the value we propose is a little bit unlikely to be accepted in the target distribution, okay? Normally we would just kind of reject this, right? We would just say this value you proposed, according to the target distribution, it only happens so often. So often we will reject it, but we might kind of boost that value if our proposal distribution says is also unlikely to propose that, right? So if our proposal distribution will very rarely generate the number 3, then whenever it does generate the number 3, we have to give it some consideration. Okay, we want to give it a little bit of special consideration, kind of taking into account how likely or unlikely the proposal distribution is to generate that. Okay, so this is kind of based on the target PDF multiplied by kind of the relative proposal probabilities. Okay. So for example, perhaps, so I mean, there's something to this in real life as well, right? So let's say you talk to friends about like movie recommendations, right? And let's say you personally do not like horror movies or something like that, okay? So you personally don't like horror movies, and you have a friend that loves horror movies, and so they say, oh, you should watch this whatever movie, right? This horror movie that just came out, and you're like, no thanks, I'm not gonna, you're just gonna reject it because that friend constantly recommends horror movies to you, okay? On the other hand, you might have another friend that also does not like horror movies and so would never recommend horror movies in general. However, if that friend that normally doesn't like horror movies comes to you and says, I normally don't like horror movies, but I really liked this one particular horror movie, you will give it special consideration because you know for that person who's generating recommendations, okay, which is what we're turning them into equations here, right? We're saying they would rarely ever propose this horror movie or something. But because they did, and we know that this is a very unlikely case, we should give it a greater weight. We're gonna give it some higher specification. And so we might accept it a little more. So that's what the Metropolis Hastings algorithm is basically saying. It's saying you can have a proposal distribution that's not symmetric, okay? You're more likely to recommend this versus this, or you're more likely to propose these values than these values. Fine, okay? We'll accept that, right? And it's just whenever this distribution proposes a value that's very unlikely, okay, we're going to adjust for that. We're going to put that small value in the denominator to kind of boost it up high. Okay, so that's the Metropolis Hastings algorithm. I guess I can do a quick coding example of this. just to kind of see how this works. I've got 7 minutes and I haven't actually prepared any code for this. So we'll see if this is even possible to do. And then I guess on Friday we can look a little bit at the math to kind of demonstrate that this works, that mathematically it balances out. Okay, so let's say, what should our target distribution be? Okay, so our target PDF will just be the normal distribution. Okay, so we'll say the target PDF, I guess, will be a function of x, and the value it returns will be d norm of x, and let's say we want, let's just do the standard normal. Okay, so target PDF is a function. I guess I'll call this p. Target PDF is standard normal. Okay. All right, so G is going to be a function of x at time t. And I guess we'll do random uniform from xt minus 1 to xt plus 1, right? So here we're just going to generate, we're going to propose one random value. So I'm going to say runif, I want one value from xt minus 1 to xt plus 1. Is that all right? So we're going to just generate, so G, okay, actually, I'll call this propose. Propose will be this, and I guess we'll just do the Metropolis, not the Metropolis Hastings algorithm. Okay, so Metropolis algorithm. All right, and okay, and so I'm going to start at, say, negative 30. All right, so what do I do? Okay, so the steps are propose x star, and then calculate p move, generate a u to decide to move or not. Okay, and then all right, so I'm going to call I guess I'll start just a train of values. We'll start off with numeric 0. Okay, and all right, so we'll do this for I in 1 through 1,000. Okay, we're going to start by so I'll say x at time t will be our start value. Okay, so we're going to propose xt, and we'll call this x star. So we call the propose function, and it will give us an x star. And then I'm going to say p move is going to be equal to the minimum between 1 and p of x star divided by p of xt. Yeah? And then what do I do? Okay, so now I'm going to do u from runif. We just want one random u. And then if u is less than p move, what does that mean? That means we accepted. And so we'll say xt is the x star will become our next xt. And then else we did not accept, and I guess this is completely unnecessary, but xt becomes xt. All right, and then okay, and then the values that we keep. All right, and this is not best coding practices. I'm just going to append our current xt value to the values. Does that make sense as far as the coding goes? I'm just doing this on the fly. I hope I hope it works, right? It makes sense to me as I wrote this up just now. Let's see. Okay, so here's P, here's propose, here's start. Let's just make sure propose works, right? So if I propose from minus 30, okay, it's generating value. Okay, that looks like what we want. Okay, so we've got, all right, so start is negative 30. We're going to start off with an empty vector for values. And we'll go ahead and run. Okay, and it's done. All right, let's go ahead and plot let's say 1 through 1,000 versus values and type equals L. Okay, oh, look at that. Okay, so we started off at negative 30, which is a terrible place to start, right? Okay, and we see in the beginning for maybe, okay, it takes us, looks like 120 iterations or so. Okay, we finally get to this region, and now we're kind of just bouncing around. Looks like between minus 3 and plus 3, okay? And so, let me just do values, and I'm gonna just, let's look at values like 120 through 180, okay? Okay, all right, well, okay, so let's just throw away everything before 120, okay? And then let's make a histogram of this. And we're hoping that this histogram will look kind of like the standard normal distribution. Let's see. It does, look at that, okay? So we generated, right? So we started off at negative 30 and we started at this terrible location, right? Like if you just had to generate values from the normal distribution, you know negative 30 is a terrible value, right? So we started off there, and the Metropolis algorithm says, you know, just started off and it just kept proposing values going, you know, between one less than that number and one higher than that number. And basically, you know, there was a time where it looked like it kept proposing values smaller and it kept rejecting all of them. And we finally got into this zone. And once we were in that zone, the values that we were proposing either get accepted or rejected, and overall, this looks a lot like the normal distribution. Okay, so that's the Metropolis algorithm, and I guess we could look at a slightly, I don't know, something. All right, we'll take a look at the math on Friday. All right, we'll end there, and we'll see you guys then.